Given the industrial interest in the use of CAF20 for use in CO2 capture from humid flue gases, it is inevitable that researchers would also examine the feasibility of CAF20 membrane constructs for CO2 capture. Indeed, one of the first papers has just been published in Chemical Communications. This paper discusses the preparation of a PBAX-based mixed matrix membrane for CO2 capture from humid flue gases. I would like to examine the workings of such a membrane construct for CO2 capture by examining in detail the influences of thermodynamic non-idealities and thermodynamic coupling on mixture permeation fluxes. For background information of the details of membrane permeation, I would like you to examine my previous video presentations on transient membrane permeations, zeolite membrane permeation, uphill diffusion in CAF20 on my YouTube channel. The description of thermodynamic non-idealities is contained in the two papers of mine cited here. I consider transient permeation of CO2 nitrogen water vapor mixtures across a CAF20 membrane with a membrane thickness delta that is taken to be 50 micrometers. The mathematical description of the development of the component loadings Q sub I as a function of Z, the distance along the membrane, and time t is given by this partial differential equation where n sub I represents the permeation flux of component I. This permeation flux is described by the Maxwell-Stefan diffusion formulation as being proportional to the gradient of the chemical potential, and the component diffusivity is d sub I. The gradients in the chemical potential may be related to the gradients in the molar loading by introducing a matrix of thermodynamic correction factors that is given by this expression where F sub I represents the partial fugacities in the upstream compartment of the membrane. The thermodynamic correction factors are determinable from the expressions for description of mixture adsorption equilibrium. I use configurational bias Monte Carlo simulations for the mixture adsorption equilibrium, and the CBMC data show that the mixture is strongly non-ideal and requires the quantification of deviations from ideality, and in this particular case I use the NRTL model for quantification of the activity coefficients in the adsorbed phase. In the Maxwell-Stefan diffusion formulation for the permeation fluxes, the intra-crystalline diffusivities of each of these components is determined from MD simulations. The modeling of membrane permeation is discussed in detail in the papers listed here. You may also watch my presentations on transient membrane permeation, zeolite membrane permeation, diffusion in ordered crystalline microporous materials on my YouTube channel. The details of the modeling that I will present here will be published in a paper that will be published later on. I will just show you the results for the permeation fluxes for a specified set of conditions. I consider first a mixture of carbon dioxide, water vapor, and nitrogen, in which the total pressure in the upstream compartment is 200 kilopascal, and the partial fugacity of nitrogen is 160 kilopascal. The water content corresponds to a humidity of 25%, and this will specify therefore the partial pressures of CO2 and water vapor. Using the Maxwell-Stefan formulation and the RAST for mixture adsorption equilibrium with NRTL parameters determined from configurational bias Monte Carlo simulations, I solve the partial differential equations and to determine the permeation fluxes for water, shown by the blue line, carbon dioxide, red line, and nitrogen, green line, as a function of square root of the time in seconds. We note that the permeation fluxes of water vapor and CO2 are about 2 orders of magnitude higher than that of nitrogen, indicating that CAF20 is an excellent candidate for use in CO2 capture from humid flue gases. A further point to note is that the approach to steady state, the water permeation flux exhibits an overshoot, and this overshoot is a manifestation of the phenomenon of uphill permeation. This uphill transport of water vapor, wherein the permeation fluxes exceeds that at steady state, is caused by the non-ideal the thermodynamic coupling effects and the off-diagonal elements of the matrix of thermodynamic correction factors gamma sub ij. These are determined from the RAST. If I use the IAST for determination of the mixture adsorption equilibrium and the calculation of thermodynamic coupling influences, the permeation fluxes are significantly different. This is because thermodynamic non-ideal effects are significant in CAF20, as I have discussed in several earlier video presentations on my YouTube channel. The message to emerge here is that CAF20 is ideally suited for CO2 capture from humid flue gases, but beware that for accurate estimation of permeation fluxes, you must account for thermodynamic non-idealities, and you must also use the Maxwell-Stefan diffusion formulations and be certain to include thermodynamic coupling effects in your model calculations. Without proper accounting of thermodynamic non-idealities and thermodynamic coupling effects, the estimates will be poor and perhaps unusable. Also examine the feasibility of CO2 capture from humid natural gas. Here are the simulation results for permeation of CO2 water and methane across the CAF20 membrane, in which the total fugacity in the upstream compartment is 500 kilopascal, and the partial fugacity of methane in the upstream compartment is 400 kilopascal. I simulate results for water content that corresponds to 25% relative humidity. This specifies the partial fugacities of CO2 and water vapor in the upstream compartment. The permeation fluxes as a function of square root of time are plotted here. Red shows CO2, blue is for water, and green is for methane. These are the calculations in which thermodynamic non-idealities are taken account of using the NRTL model and the RAST for mixture adsorption equilibrium. Also included are the influences of thermodynamic coupling, wherein the off-diagonal elements of gamma sub ij are significantly different from unity. The results show that the permeation flux of CO2 is about an order of magnitude higher than that of methane and water vapor, implying that the CAF20 membrane may also be used in capturing CO2 from humid natural gas streams. As observed in the earlier slide, the permeation flux for water exhibits significant overshoot, implying the occurrence of uphill permeation. This uphill permeation is caused by the non-diagonal elements of the matrix of thermodynamic correction factors. If thermodynamic non-ideality effects are completely ignored and calculations are done on the basis of the ideal adsorbed solution theory, we observe that the permeation flux for water vapor is significantly higher than that of CO2. These results are quite different from the results obtained using the RAST. The important message is ignore thermodynamic non-idealities at your own peril.